part didn't get captured the previous meeting slides, the PDFs 17 and 18. We are in 18 right now, so we stopped until here. Now I will continue from here. A directional derivative. I just told what directional derivative was in the previous part of the video. Directional derivative. You just want to find the change of the function value in some direction other than the gradient. How do I do that? You just have to do the dot product of gradient along the direction. That's it. Nothing much to be done here. Since you're doing the dot product of two vectors, you will get a scalar quantity. So that's why directional derivative is a scalar quantity, nothing much. Okay, let me just verify it once again. Okay, yes, it is being recorded. Okay, yes, it's the same function. If you not same, but probably similar. Is it the same function? Uh, It looks circular, but it is not circular. I think I don't know if it's the same function. It's not supposed to look like this, probably. Maybe I don't know. Maybe it's an elliptical function or something. Like this, I'm talking about this one. Is the cross section and ellipse or is it a circle? I was thinking about that. Yes, okay. This is an ellipse. This is an ellipse, I suppose. Anyways, so directional derivative. If I draw the contours of this function, I am assuming it's an ellipse, so I'll draw the contours like this. The contours will look like this. Assuming the contours will look like this. Okay, fine. The direction of maximum change will be perpendicular to the contour lines. Nice. I want directional derivative. So if I have some random direction, let's say I want to find the direction, I want to find the derivative along this direction. How do I find that? I just have to do the dot product and I will get this one. Because what is the meaning of dot product of two vectors? I'm just finding the component of one vector along the direction of another vector. So basically, I'll get this value, whatever is this magnitude, I will get the magnitude of that. Dot product of two vectors will give me a scalar, so I won't get a vector back. I will just get this magnitude, the magnitude of the gradient vector along the vector that we are interested in. Here in this case, it is u direction. Enough of directional derivative. I mean, we did discuss directional derivative in the previous video as well, which unfortunately has not been captured. Same thing again, but now we have this is vector notation. This is in terms of matrix. So dot product of two vectors is basically, let's say if you have two vectors, I can simply write it as A matrix transpose multiplied with B. That is what is happening here. So gradient column matrix, whatever is this column matrix, transpose the other column matrix. You'll get your dot product. It's just the matrix representation, left side your vector representation. Examples. See, this is what I'm talking about. Matrix representation. The direction is given to be 1 comma 1. But I did mention, do keep bear in mind, I think I did mention this u is, it's supposed to be it's supposed to be what is it called, unit vector. This is not a unit vector. That is absolutely not a unit vector. Then what is this? What is this? Sacrilege, I don't know. This is a sacrilegious act or something. I don't know what is this. How do I term this? I don't know. I don't find the words to describe this. Let me verify it once again. And I mentioned that u must be a unit vector, but in this case, u is d here. D is not a unit vector. There might be a mistake. Directional derivative, unit vector. Let me verify it for you people. Yes, it should be a unit vector. So this slide is wrong. What you're supposed to do is you're supposed to take u should be the unit vector of d. So how do you find unit vector of d? You just divide it by It's whatever is its magnitude. What is its magnitude? 1 square plus 1 square under root. It is 1 by root 2. So this is my u. This is my u. This is a unit vector. So the final answer divided by root 2 is your correct directional derivative. So this is wrong. You need a unit vector. I mean, okay, direction is fine, but u should be a unit vector. So it should be d by root 2. Good. Critical point. Critical point is just like an extreme point. If the gradient is 0 at any place, gradient is a vector, so you simply can't write 0. 0 bar vector equal to vector. 0 bar is a null vector. So if the gradient is a null vector at any of the any places, any place, whatever it is, that place, that point is called a critical point. That's it. Nothing much here. Local maxima, minima. Yes. So critical point, it is either a maxima or a minima. Local maxima or local minima. Or can it be a saddle point? Maybe it could be a saddle point. So it is either a saddle point, or it is a maxima, or it is a minima. It could be any of these three things. So we will look at those possibilities. Okay, yes. This is 2D. R2, X is my input, Y is my output. How do I okay, how do I find a saddle point? Saddle point is basically this one, point of inflection. I was talking about point of inflection. No? Basically, the point at which your curve changes from convex to concave, or concave to convex. Here, from concave, it's becoming convex. So, the point at which this is happening, that is called saddle point. You can think of it in this way as well. In mathematical terms, double derivative at that point is 0. So, dou square f by dou x square is 0 at this point. Saddle point. This is the interpretation. The point at which the concavity or convexity changes. That is a saddle point. Local optima. Okay. Local optima. I see. If in a neighborhood, if the point has the least z value, it's a local minima. Local maxima, opposite. In a small neighborhood, if some point has the highest z value, it's a local maximum. Global maximum, global minimum out of all points. Sometimes you can't have global maximum. For example, if you have something called, if you have this function in 2D, how will it look like? It will just keep on going. Where is the global maxima? You'll never find it. If you find some place, you will find a better place. You can keep going upwards. So there is no global maxima. So there is this thing. If you have a convex function for all x values, so if you have a convex function, for sure you will find a global minima. Global maxima, it won't be there. If you have a concave function, you can say there is a global maximum. Concave function. There's no global minimum because it keeps going down. Saddle point is somewhere in between. Something like, we'll get something like this. It's concave on one side and convex on the other side. It can be like this. Even in sin x graph, we have points of inflection. Somewhere over here, it's concave at one point and suddenly it becomes convex. So wherever the convexity concavity changes, there you will have the saddle points. Anyways, steepest ascent, steepest descent. Hmm. Concave gives maxima, convex gives minima. Yes, that is why when we are doing, uh, when we are trying to find the maxima and minima of a function, first what we'll do, we will assign the first derivative to be 0. And then what we will do, we will check if the double derivative is greater than 0 or not. If this is true, it means it is minima. Why is the greater than or equal to 0 giving minima? Because this means it is convex, and convex will give me minima. That is the reason. Same thing for this one. If your double derivative is negative at a critical point, if it is negative, then I can say that it is a maxima. Why is that the case? Because this condition will give me a concave, con- the function will be concave at that point, and at that point I will find a maxima. So concave will give me maxima, convex will give me minima. So all these years we've been doing this. Also one more thing, isn't steepest descent and ascent already covered in minor one? That is for linear programming. We are in non-linear programming at this point. That's where we have all these gradients and things coming up. We are in non-linear programming at this point. Steepest ascent, steepest means you're supposed to move in the direction of your gradient. Ascent means along the direction of the gradient. Descent means opposite in the direction of the gradient. That's it. There is no other meaning here. Because I told you, gradient will give you the direction of the maximum change. There is matrix representation here, or else you can simply write gradient of f dot u. That also works. Okay. What else is overall possible unit length directions? Okay. Okay. Nice. This is what I was talking about. You just take a small step in any direction. The the direction in which you get the maximum change is along the direction of the gradient, and the opposite. If you're if it's decreasing, maximum. If you're getting maximum decrement, that is in the opposite direction of the gradient. Maximum increment in the direction of the gradient. Maximum decrement in the direction opposite to the gradient. What is decreasing? Your function value. Function value, if it is if it's a function of x comma y, it will be along z axis. If it is just a function of x, it will be along the y axis. Okay. Okay. What else is there? Recall that. Okay. This is just a dot product. This is just a matrix representation. It's just p bar dot q bar. I know p bar dot q bar is length of p, length of q, cos theta. I know this. This is just a dot product. But to scare you people, they just mentioned it in the matrix representation. That's it. Or else, if you're comfortable with matrix representation of vectors, it is fine. None of this will scare you. And this is the instead of writing something like x1 square plus x2 square so on till xn square under root, they simply wrote this in matrix form. If I change this matrix form, I will get something like x bar dot x bar. Same story. You get it, right? That is how you get x1 square plus x2 square and so on. Mm, yes, this has to be true always if you want to find directional derivative. Any results over here? Oh yes, the direction of maximum change is this one. D, in this case, D is a unit vector. D is a unit vector. Unit vector means its length is 1. How do I get a unit vector uh, which will show me the maximum change? Just take the gradient. Gradient will give you direction of maximum change. How to make it unit vector? Divide by its norm, divide by its magnitude, you will get this one. So nice. This is okay. I think the next slide, from the next slide, it's like main thing. Before slides, I don't know. I made a big blunder. The video didn't get captured. Let me verify it once again. Is this being recorded? Yes. Thank God it's being recorded. Okay, sorry. Why is this very non-linear programming? We did. I mean, not all of us. Some of us did go through PDFs 17 and 18. All of that is necessary. Not all of, at least some of them. At least some of them are necessary. So even if you did miss them, you don't have to worry. It's just some uh, calculus and vectors. That is what we looked at. Some concepts of convex, so many things we just looked at. Maybe you could go through them and try understanding them by yourself. Okay, non-linear programming. What is non-linear programming? See, it's the same thing as linear programming, but instead of in, instead of a linear function, your objective function will be some non-linear function. So, mm, for example, instead of having like 2x1 plus x2, you'll have something like 2x1 square plus x2, non-linear. So that's it. That's the only difference. Everything is ditto, same to same, but your objective function looks non-linear. That's it. That's the only change. Mm, okay. Okay, fine. I Even the constraints. Look at the constraints as well. Your objective function is very much linear, but the constraint is non-linear. This is also non-linear. So is this non-linear? Yes. So what do I do? Yes. So not only the objective function could be linear, but even if constraints are non-linear, then the problem becomes a non-linear programming problem. That's it. Okay. Constraints are non-linear. Are you are you sure though? Let me just see. General form. Okay, they did mention f and the constraints, the objective function or the constraints. If any of these is non-linear, then the problem becomes non-linear. This is an example where function is linear, objective function is linear, but constraints are non-linear. Okay, your objective function is non-linear, but constraints are very much linear. See how you didn't get a straight line because your objective function is non-linear. That is why you got this one. In the previous case, my objective function is linear, so you will get linear lines. If you remember, during graphical method, we used to assign z values, no, z equal to 0, z equal to 1, z equal to 2, and so on, something like that. Here also some person is doing the same thing, z equal to something, z equal to another thing, and so on. What is happening here? I think here at this point, z equal to 857, that curve is it's like it became a tangent to this line. Maybe that's why it became a solution. At least that is how it looks like to me. It's touching the point at that point. If that makes sense. Anyways, isn't the line the tangent? No, I'm not telling this line is a tangent. I'm telling at this point it is tangential. I'm not telling it is a tangent. If you zoom in closely, it looks like a tangent. It's like it's touching the point, just this point, no other point it's being touched. It's like you have some curve here. At this point, the line is being touched only at one point. So the curve is tangential to this line. Or else you can think of this like this. This line is tangential to this curve. You can think of it like that. The other way around. Tangential means it's only touching at this point. So that will give me my optimal solution. Maximization. So 857 is giving me a nice value. If I increase my 857, then I will get something like this. It will not touch the feasible solution. Fine. This is non-linear. Okay, constraints are non-linear. Interior optimal point. Okay, in linear programming, what we did, we kind of declared that all the optimal solutions will be on the corner points, and my job is done. But here, if you look at it, this is one example of a non-linear programming such that the optimal point is inside the feasible region. The optimal point is inside the feasible region. So now we can't sit at the corners of this region and keep searching for the optimal solution. That is not feasible. That is anyways, that is not what you're going to do. So Basically, these examples are telling you how strange is not how strange, how different is non-linear programming from linear programming. Unconstrained optimization. Given some function which is differentiable, how do you find its global minimum? I mean, we did kind of discuss, no? If I can declare that the function is a convex function, then I can say there is a global minimum. But they didn't give any of that. They simply told if it's a differential function, how do you find its global minimum? Hmm, gradient. If gradient is zero at any point, okay, I think, are we answering this question? No, I think we will be soon answering this question. Given a function stationary condition, what does it mean? If the gradient is zero at any point, we did look at it. No, it's a critical point. So it could either be a saddle point, it could be a local maxima, it could be a local minima, or it could just be a straight plane whose value is never changing. So even its gradient is zero, zero bar. Sufficient minimum criteria. If this one, this reminds me of, this is the Laplacian, right? This Laplace. How do you get Laplacian? You just, Laplacian is given by this one. Dou square f by dou x square, comma, dou square by dou y square. It's okay. Let me write this here. If my function is a variable of x and y, what does x star represent? I mean, see, in the previous, if you did attend the previous lecture, the first video, if you find any x, then see, x star is basically some x value. That's it. But it's some value over there. It's basically telling that x is equal to x star. That's it. Some value is there because it need not be for all x values. For some specific x value. Okay, you got something. Okay, I did see the chat. No worries, the chat is not being recorded. Only the video is being recorded. So only the people in this meeting will know what you typed. Anyways, uh, okay, where was I? Okay, if your function is a function of two variables, what was I telling? Ah, Laplacian. Laplacian of this function will be dou square f by dou x square plus dou square f by dou y square. I think. I think this is the Laplacian. Mm, yes, this is the Laplacian. Yeah, this is the Laplacian. It reminded me of divergence. Divergence. Divergence is very similar. No, you'll get dou f by dou x plus dou f by dou y. But we are not doing this. Here double derivative. So this is Laplacian for two variables. What is positive definite? What is negative definite? We'll see. I hope they will give us what does that mean. But this is very similar to the two-dimensional case. In two-dimensional case, if double dash is greater than or equal to zero, it means it is convex, no? And I can say it is minimum. So very similar. It's like this is very similar to double derivative, Laplacian. See, Laplacian double derivative, very close. So you can remember it this way: minimum criteria, something should be positive definite, which is the Laplacian. Maximum, this should be negative. I mean, it reminds us of this one, no? In the 2D case, if double dash is negative, it means at that critical point you have a maxima. This is not n, this is double derivative. Okay, now how do I know positive definite, negative definite? I hope they'll tell us what it is. I don't know, I didn't see it. Okay, they're not telling us. I mean, positive semi-definite, we do know. How to know positive semi-definite? If the function, if the matrix has uh, non-negative eigenvalues, then the function, then the matrix is positive semi-definite. right? Does this have eigenmatrix? The eigenvalues though. Why does it say neither positive semi-definite nor negative semi-definite? Is there a problem? Uh, in the previous, okay, someone has something in the previous slide. Yes. In that time, I will check what is positive definite, positive semi-definite. You're asking something, right, Ayush? In way, can we say we are checking for it's like yes, yes, something like that, convex or concave. Yes, yes, something like that. Because I did mention, no, Hessian. The interpretation of a Hessian matrix is the curvature. How is it curved? And Laplacian, I think, is very similar to that. I don't know. We'll see. I'm just looking. Negative definite. If okay, I found some matrix representations there. I found some matrix. It's like if you have if this is true, it is negative semi negative definite. If equality is also there, it is negative semi definite. We looked at the matrix form of that, no? There in that slide for Hessian matrix. I'll show you. I mean, those who did not or could not join the meeting, you must have missed this part. Where is this part? This was Hessian matrix, no? Where is Hessian matrix? Hessian, 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 Hessian. Hessian, Hessian. Where is Hessian? Yes, here. Not here. Here. No, no. How, where is this? This is Hessian, that is fine. Where is the condition? No, it's in the previous slide. Ah, here. I was talking about this one. So this is what I found. If this is greater than or equal to zero, it is semi-positive definite. If it is strictly greater than why is this? If it is strictly greater than zero, it is positive definite. If it is less less than or equal to zero, it is semi negative semi definite. If it is strictly less than zero, it is negative definite. But what is this v? V is for all vectors. What vectors? Okay, apparently we will have more about this later. Okay, anyways, going back. Now I got some clarity. What is positive semi-definite, negative semi-definite, and so on. Where was I? 19. Okay. Let's see if any example is going to help us. This is again the Hessian matrix, no? I think this person is not trying to denote Laplacian. I think this person is trying to denote the Hessian matrix or something. I think same notation but different meaning. This is Laplacian. I think this is Hessian. I think this is Hessian. So Hessian and Laplacian are different. Hessian is a matrix. Laplacian is a scalar number. We are looking at the Hessian only. How do I find? Does anyone remember what are the eigenvalues? Since it's a symmetric matrix, I think I can declare that my eigenvalues are 2 and minus 2, right? Does anyone remember eigenvalues of a symmetric matrix? Does anyone remember? No, eigenvalues, you will only get some of them. Not all four of them are eigenvalues. Okay, let me just look at this. Probably it will help us somehow. I am thinking the eigenvalues are whatever is in the diagonal. It is not non-negative. Mm, okay. How do I check if this is positive semi-definite or not? I told you, no, if there is something like this, some V transpose HV, positive semi-definite. Semi-definite means it is greater than or equal to 0. Okay, what is V? V is apparently any non-zero vector. So you can take any non-zero vector. It will work. Let me take some AB. So it's like A. Um, okay, 1 minute. I think someone did enter my room. Okay, fine. Yes, anyways. V is all vectors. Huh? Okay. Okay, since we are running out of time, you just look into this. But this is the definition for matrix H being positive semi-definite, and V can be any non-negative. Not any, it should be all. All non non-zero, non-zero, non-null vector. So it's like if you find two vectors V, like let's say V1 and V2, and for some V1 you get greater than or equal to 0, for some other vector you get something else. So I don't think it is going to satisfy any condition. So you can't tell it is either positive semi-definite or negative semi-definite. Or else you can directly look at the eigenvalues. If all eigenvalues are, what was the condition again? Non-negative. If all eigenvalues are non-negative, then it is a positive semi-definite matrix. But why is this person telling it's an indefinite matrix? Indefinite, indefinite matrix. I'm just googling that. If non-zero vectors and wait, why is this person? How nice. A symmetric real matrix which is neither positive semi-definite nor negative semi-definite is called indefinite. When is a matrix negative semi-definite? If all my eigenvalues are non-positive. Okay, okay, I think I got it. Here all my eigenvalues are not positive. All my eigenvalues or not negative. One is positive, one is negative. Assuming that in a symmetric matrix, I think in a symmetric matrix, my eigenvalues are the diagonal elements itself. All of them are not negative, all of them are not positive. So it is neither positive semi-definite nor negative semi-definite, hence it is indefinite. Yes, nice, good. We have clarity now. I think we have more clarity than anyone else who's probably looked at this slide. Hopefully, if you've gotten what I told, you can. This is another way to verify. You can verify it mathematically, but you can just look at eigenvalues and make our lives simpler. Some graphs. Okay, okay. Uni model. Okay. Function with significant null space effects. Essentially unimodal functions. Functions with huge number of significant local optima. Function with small number of significant local optima. Functions whose global structure provides no useful information about its optima. Why does this feel like it's a meme? Anyways, there's some functions. Okay, Rosenbrock function, whatever this is. What is it telling us? Okay, it's a special function probably, some special function. Okay. Methods for unconstrained optimization. First derivative method. Gradient. There should be routines. Okay, this telling that we'll use derivative, first derivative, second derivative, or no derivative. There are so many methods. Okay, we'll see what are the methods. First derivative methods. Line search, trust region methods. Okay, I don't remember reading any of this, so we'll see. I will read it along with you. Line search versus, oh my goodness, line search versus trust region. Algorithm starts from an initial point. Okay, algorithm starts from an initial point. Selects the search direction by either a predefined formula or by search finder method. I don't know what. I think there are two different ways to find a direction. Let's say you found a direction. Let's say this is the direction. This is the direction. Let's call it P. P bar in case it's a vector. I mean, direction is a vector, right? Uh, then finds a step size that minimizes the objective function within the direction. So, okay, this looks like a minimization problem because minimizing the objective function, it's a minimization problem within the direction. So, what do you want? You're somewhere at x1, you want to go to x2. Where is x2 in the same direction as that of p? How do you reach it? Probably you just, so x1 plus alpha p, alpha is some scalar, so x1 plus alpha p will give me x2. We will see this is the same thing that will appear in the methods that we are going to do now. So this is the essence. You start at one point, then along the direction of p bar you take some steps, so the length of the step will be alpha. Then you'll reach a new point, and then we'll see. That is the line search approach. Finds a step size that minimizes, moves along the search direction to find, and it keeps going on. It's like towing. It keeps going on depending on the function, and we'll see. Trust region approach. Trust region methods create a trust region around the current iterate. A model that is a good approximation of the true objective function in the trust region. Get the new iterate by optimizing or iteratively optimizing the trust region size. I think it's something like, I don't know. You have a point, and then it's creating some region around it, and it's doing something in that region. We'll see. I think they will explain the process to us. In line search algorithms, a line search is carried out along a search direction in each iteration, and trust region algorithms obtain a new iterate point by searching in a trust region. Okay, I think what trust region is doing is it will take a very small neighborhood. Will take a very small neighborhood, and it will walk in all directions. I think it will walk in all. I think this is what is happening. It will walk in all directions and find where is the function changing maximum. If it's minimization, so where is decrementing? If it's a maximization problem, where is it incrementing? I think that is what is happening here. In line search method, use efforts to generate a search direction and then focus on finding a suitable segment. Trust region methods define a region around the current point within which the within which choose step and direction to be approximate optimized. Okay, I think that is exactly what is happening here. In line search method, what we'll do is we will first find the direction, then we will find the alpha, then we will get our x2, and we'll keep doing this process for many times. How to get the p, how to get the alpha, there are many methods. We will see, it is there in this slide probably. Trust region is, I think, it's like in a small neighborhood, it will just go everywhere and see where is the best possible solution. I think that is what is trust region. We'll see. I think I might be wrong, but we'll see. Line search. Okay, yes, I think this is very much nice. Trust region versus line search. Line search is, let's say you're at x1, you did some, you applied some algorithm, you will get some direction p. Let it be straight. Get some direction p. Now you have a direction. How much should you walk in this direction? That will be given by the scalar alpha. So if you do some, vector, how to use vectors, my new point will be nothing but initial point plus alpha into whatever is this direction. That will give me the new position of x2. That is line search. Nice. The other method is trust region. I think what it will do is it will declare some region around it, some small neighborhood. I think it will check somehow. I don't know what algorithm it's applying, but it will only be within this region. So my next point will be within this region. Then it will create a new trust region and it will move only in that. So something like that. I think that is how it works. Okay. I see contours of f. Okay, fine. I think some algorithm is using this contours and finding something. How do I go down? How do I go up? There'll be more clearer okay, line search methods. I think in this slide there is only line search, and even in the following slides there is line search. So I don't think trust methods will appear anytime soon. Generic line search. Okay, minimization problem. We want to minimize our objective function. Pick an initial iterate x naught by educated guess. Okay, basically telling pick some random x. Not very random. Hopefully that is close to the minimum. But whatever you pick will not be the minimum. No. Minimum is very, you can't pick it. It's somewhere over there. It's hard to pinpoint. So pick a point that is close to the minimum until xk has converged. Okay, what we're doing, we're iterating. So from x0 we're going to x1, we're going to x2, and so on till xk. So until xk converges to the minimum, wherever is the minimum point, it has to go till there. I mean, exactly, it's not possible. Maybe we'll see. I don't. We'll see. Calculate a search direction pk from xk, ensuring that this direction is a descent direction. Since we are minimizing, our rp will be nothing but the descent direction. So how do I get a direction that is in the opposite direction? Gradient into some direction should be negative. Basically, p is a negative direction. That's it. If I substitute p with some vector opposite to the gradient, so this value will be negative. Okay, so that for small enough steps away from xk, the direction pk, in the direction pk, the objective function will be reduced. The same thing, see, x2 is a new point, some alpha p. If p is in the opposite direction of the gradient, it means you're going down. Let's say this is the function. Let's say you're here. Gradient will show you a direction that will take you upwards, but then opposite of the gradient will give you a direction that will take you downwards. I mean, negative of the gradient is not the only direction. There are many other ways. We will see. We'll see. They will come up. They will come soon. I don't know where is that. Okay, you'll basically point one is find direction. Point two, find step length. Some alpha. Alpha one, alpha two. In this case, this is alpha one. Yes. Alpha should be zero, not zero. Alpha should be a positive number. Because if alpha is zero, it means you did not move anywhere. If alpha is negative, it is pointless because the sign will be taken care of by this direction. You don't have to worry about the sign. So alpha should be strictly positive. That is why it is given here. Step length. Okay. See, this is what I've written. So x, if k is 1, so x2 is nothing but x1 plus alpha 1 p1. That is what I wrote here. Oh, sorry. So you iterate, you keep iterating until xk converges to the minimum. We'll see. There are some conditions for that as well. How do we check? Okay, this is some random contour. We started at this point, I think. We came here, 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 here. I mean, if you look at this equation, this is we are just walking linearly. We are not walking non-linearly, but our function is non-linear. So that's why we are taking steps like this, linear steps. We are not taking any curved steps or something because our new point is some linear combination of something. Linear. It's very much linear. No non-linear here. That's why all these will be linear, straight lines. Okay, there is some method called gradient search. When is it called gradient search? When the direction that you take is the negative of the gradient. So this is one method. This is another method. You just randomly go somewhere, go here, 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 here. This is some method, but okay, okay. They did get alternating x and y directions. So it's like uh, go in the direction where x is decreasing. So he will search in this direction. Is it right or left? It is decreasing left. So this person will go left. At some point, he'll come and stop. Next question he'll ask is, where is y decreasing? Is it up or down? Answer is down. So he will go down until a nice spot until it decrease so much so that after he steps more than that it's increasing. So he will stop there only. Now next question, where is my x decreasing? Where is my x decreasing, left or right? This is the meaning, alternating x and y. So first he will check for x, then he'll check y, x, y, x, y, and so on. This is one method. So alternating x and y directions is this algorithm. Is y decreasing? If yes, in which direction? Go there. Is x decreasing? If yes, which direction? Go there. So on and so forth. That was the first method. The second method, gradient search. What is gradient search? My direction is directly this one, negative of gradient. Negative of gradient will give me the direction of uh, maximum decrement. So gradient will give you the direction of maximum change, specifically maximum increment. Now instead of increment, now you'll have decrement. Minimization problem. So we are good to go. So how will it look like? It will keep going down like this. It's almost perpendicular to the contours, right? If you notice, why is it not exactly perpendicular? Because we took the gradient in this direction. So it at this point the contour will be perpendicular to the gradient. At this point the gradient is different. So that is why it's not perpendicular here. Because it is perpendicular here, not anywhere else. Here the gradient is different. Why is this happening? Because you are moving linearly, you're not moving non-linearly. You're not moving in the gradient direction. Let's say the gradient looks like this probably, or let's say the gradient looks like this, but we are not walking in that direction. They're not probably straight lines. They're not exactly straight lines. It depends. I don't know. This plot some 3D graph, you will understand. After taking okay, in the context of gradient search, this is p, length is alpha 1. Stop here, find the gradient, negative of the gradient, you'll get p2. You take a step of alpha 2, stop there, find the new direction, negative of the gradient, alpha 3, you take steps, you take a step length of alpha 3, and so on. Keep going until you reach minimum. You might never reach minimum, but it's fine. You can stop just beside the minimum. That is not a problem. Okay, it is being recorded. Fine. Another, okay, this is without the color. Importance of step length. Okay, okay, yes. So if your alpha is very small, it will take a lot of time, take a lot of time to come here. And if your alpha is very big, from here you will step. It's noticeable, right? If alpha is, for example, okay, fine, that is 2D, no? Let's take this 3D. If you start here, if your alpha is big, the gradient descent is okay. Let me stand you. If your alpha is big, you will reach somewhere over here. Then from here, you're supposed to find gradient. It will be somewhere over here. Keep going. Same thing is happening here. If alpha is very small, it will be like you'll go keep going very slowly. So the problem here is how do I find the best, not best or the better, the good, whatever step length. Wait. Okay, something happened here. The proportions. 1 minute. Okay, I think now the proportions are right. Is it possible to adjust this? Okay, fine. It's fine now. Okay, here is our cheat sheet. Cheat sheet in the sense, basically, what we're doing, step one is you have some function and you want to do some iterations over it. First step is in line search, you're supposed to choose a direction. Choosing a direction, there are many ways. Uh, there is gradient search, or else you can do the alternating x and y. There are multiple ways. After you've chosen your direction, you have to compute your step length. What is the step length that you're supposed to take? Here in this case, it is a maximization problem. So your direction will be the gradient in gradient search. What kind of a step length am I supposed to take? You're supposed to take a step length such that this happens. So from xk, if you walk to a point in the direction of pk, where the step length is alpha k. So now you reached a new point, which is xk plus alpha k pk. The function value at that point should be more than the function value at your previous point. This is a maximization. We just shifted to a maximization problem. So how do I select such an alpha? Many ways are there. Many ways are there. Okay, after you chose your step length alpha using one of the ways, the next thing is update. Okay, since we are iterating now, our new point is xk plus alpha k pk. I'm writing it as xk plus 1. Now I have to check if my xk plus 1 is an optimal solution or not. So there are three conditions. What are those three conditions? If my xk and xk plus 1 are very close, then I can probably say, okay, maybe this is very close to the minimum, so my xk plus 1 is the point where the minimum is there. Okay, in this case, maximum. This is maximum maximization, no? So maximum. If xk and xk plus 1 is very close, so probably my maximize near xk. For example, if you have some graph like this, so let's say some graph is like this. Let's say you start here and you go to another thing, and then you go equally. Let's say your step lengths are equal. Here your function value is something. After you moved in this direction, your function value is bigger. But after you moved in the same direction, your function value is getting bigger, but now it's getting, the change is not much. And probably after you move in the same direction in the, like the same step length, the function value is not increasing much. So it means probably you're very close to the maximum point. That is the intention. That is the first check. This is one way to check whether you're close to the maximum or not. The other way is instead of checking xk and xk plus 1, I will check the function values. Yes, very similar to what I just described. Okay, this is the second condition. The first condition is if you're not what I just told before is for the second condition, no change of value. My function values are not changing, so no change of value. No difference in consecutive points means no difference of consecutive points means let's say you started here and then you go to x2 and then you go to x3 and then x4. It's like it's in the same place. If it were in the contour, you started here, you went here, you went here, you went here. It's like you're going to the same place again and again. It's not again and again. It's like very close, very close, very close. So your algorithm will keep searching for the minimum, but it's never going to end. So you can just stop after some time. Okay, it's not changing much. I will stop here. That is the first condition. No difference in consecutive points. Xk and xk plus 1 are almost same. Second condition is the function values are almost same. Now gradient close to zero. Gradient close to zero. I mean, if you if we look at the if we look at a 2D function, let's say if it's something like this, I know my maximum is there when the first derivative is 0. Even in 3D, wherever gradient is 0, you might have what would you have? You would have a critical point. But since I'm doing maximization, since I am always moving in the direction of the gradient or whatever, so I will always be moving is in this direction, close to the maximum. So I can be sure that at the critical point, I'm saying gradient is 0. So gradient is 0 means it can be maxima or minima. But I know I'm doing this algorithm, so I will get pakka maxima. So okay, I'm getting pakka maxima. So I'm moving towards the maxima. So if the gradient turns out to be very close to 0, maybe you're somewhere over here. The gradient is almost 0. So you can declare I am very close to the maxima. I can stop my iteration over here. Only if any of these conditions are satisfied. If none of them are satisfied, no. Iterate it once more. Find p, find pk plus 1, find alpha k plus 1. Repeat the same process again. That is the thing here. Uh, okay, that is what we've discussed here. If gradient is epsilon is a very small value, so you can't put exactly 0 no, because exactly 0 means you reached the exact point. That is not possible. I mean, it will take a lot of computation power. So epsilon is a very small number. What is this gradient? Gradient is almost 0. That is the meaning. I'm taking norm because epsilon is a number. Gradient is a vector. So its norm should be almost 0. No change in function value. So if you take the difference of the function values less than some epsilon, or else you can do this also. It doesn't matter because epsilon. It's like you're taking a fraction. Final minus initial by initial. If you did some error analysis, something very similar to that, doesn't matter. You can either do this or do this. No difference between consecutive points. This is what I was talking about. If you like, you moved from here to here, then here to here, then here to here, here to here, and if there is no change, if you're just going here and there, you can stop. That is this condition. But to get accurate values or to increase precision, you're supposed to take very small e. But dealing with very small epsilon values is also difficult. So depends. But it should be very small. Exactly 0 means you get the exact answer, but that is not you can't compute it. Okay, what is this line search algorithm for minimum? Okay, everything is same, but we will see what how to decide the direction. And here you have less than, because when you go to a new point, the function value should be less than the function value at the previous point. Mm, okay, same, everything is same, but instead of greater than, you have less than here, and you have a different condition here. Whatever direction you take, if you take the dot product with the gradient, it's supposed to be less than zero because you want to go in the minimum direction. Oh, I mean, we were doing minimum, no? Or was it maximum? What is this? Okay, this is maximum. This is minimum. So in maximum, whatever direction you take, if you take dot product with the gradient, you'll get a positive number. For example, in gradient search, P is directly the gradient. So gradient dot gradient will give you a positive number. Mm, okay, this is fine. Okay, there's an example. Now we are using gradient descent, the line search. This is what we are doing is line search now. In line search itself, there are many ways to find pk and alpha k. Okay, in this case, in this example, what this person did is direction they're deciding using the gradient. Since this person wants to, what is it, minimize? Okay, we'll assume this person wants to minimize the function. So what will this person do? This person will, using gradient descent line search, what he'll do is gradient line search, he will just assign negative of the gradient. This is my function value. So find the gradient and find its negative. This is the gradient. It's negative means you get minus sign. From here we got our P. Our P is some column matrix. Column matrix are vectors. So don't get afraid. Column matrix are vectors. That's it. Column matrices are vectors. Okay, I think they've either given the initial point or we might have to find it. But let's assume they've given this initial point. Now from here we are supposed to iterate. Iterate means move along the direction of descent. How do I do that? I got my P1, which is the negative of the gradient. At this point, just substitute 1 and 1 by 2 in this. You will get this minus 3 by 2 and 0. This is some direction. We got some direction. Mm, okay, this is what I was talking about. This is our new point. New point is x1 plus some step length alpha 1 and the direction. We know our initial point. We don't know what is our alpha. We know what direction we want to move in. You add these, you'll get this one. So our new point x2 is a function of alpha. I mean, not a function. I mean, it is indeed a function of alpha. If you substitute this x2 in this one, beware, capital X2 is different from small x2. Capital X2 is a new point altogether. Capital X1 is a new point altogether. But x1 and x2 are two numbers. So basically, x1 is like some x1 1, x2 1, something like that. Small letters are just components. Capital letters are points. Don't get confused. Okay, what was I telling? If your x2 is in terms of alpha, if you substitute this point in this one, so x1 is nothing but 1 minus alpha 1 3 by 2, x2 is nothing but 1 by 2, 1 by 2, this 1 by 2, this is gone. So x2 is 1 by 2. So if you substitute that, you will get something here, x1 square minus x1 x2 plus x2 square. What is that? I know x1 is in terms of alpha, x2 is 1 by 2. So finally you will get some function of alpha, which is here. F of x2 is some function of alpha, and that function is over here. Some 1 minus 3 alpha by 1, 3 alpha 1 by 2 whole square minus whatever this is. After substituting, it's not visible here, but you can substitute it on your own. and you will see. Now, why are we doing all of this? We want to find what is our alpha, how to find alpha. Since here we have a function in alpha, just differentiate it and assign it 0. Why are we doing that? If you're doing this, it means you're trying to find the critical point uh, of the function. Where is the function? Where is it becoming a maxima or a minima? We know it, for sure. We know it's a maxima. So is this a maxima problem? We know it's going to be a minima because if you're using gradient descent, if you're going in the direction of negative gradient, for sure you will get less value only. So that's why, because whenever your first derivative is equal to 0, it can either be a saddle point, it can either be a maxima, it can either be a minima. In this case, it will be a minima because you're walking in the direction of negative descent, negative gradient. So fine, simply assign first derivative of this function of alpha is 0. You got some function in alpha, no? Just do this one and solve for alpha. You'll get some alpha values. Here you got alpha as 0.5 after you solve this. If how do I get alpha? Just solve this. You'll get alpha 1 as 0.5. Substitute this alpha 1 in this one. You'll get our x2. Now we got our x2. X2 is nothing but x1 plus alpha 1 p1. So x2 turns out to be 1 by 4 comma 1 by 2. It's not clear here, but I think that is the answer. Now optimality check. What is this person doing? This person is checking the function values. Function value of x2 and function value of x2, function value of f1, and taking the difference. Epsilon, this person set it as 0.05. You can set it at any small number. Is 3 by 16 minus 3 by 4 greater than this value? If yes, you can stop here. It means the function value is not changing much. It's not decreasing much. If no, then you have to iterate it once more. You have to start from your new point x2 and you have to find x3. So how do you find x3? This do the same method. You have this one, you have the direction. Find the negative gradient direction at x2. Find alpha by doing this method. How do you find alpha? Substitute your new point in the function, then you'll get some function in alpha, differentiate it once, equate it to 0, solve for alpha. So by the time you do this, you will have your alpha, you'll have your p, you will get your new point. New point is old point plus alpha into p. Okay, some other example is there. You have some function, you want to minimize it. You can use the gradient descent or gradient search. We are still in line search and many ways to find the direction or the alpha length. In this case, we're using the gradient to find the direction. It is given, this is the initial point. Find the gradient, negative of the gradient because you want to minimize it. So this will be your new direction. Not due, this is p1. You want to move in this direction. By how much? You want to move by alpha 1. How to find alpha 1? We don't know. So what we do is, whatever x2 is there, no? This is our possible value. We are moving in the direction of p1. This is p1. Our function is somewhere something like this, or let's say something like this. It's it's a 3D thing. So let me just, maybe our function is something like this. Whatever it is, some function is there like this. I said p1 is a direction, no? So we are fixing a direction. So let's say you are here, or let's say you are here. This is the fixed direction. So what I'll do is my x2 will lie somewhere over here. So that's why, I mean, if your imagination is nice, what how it will look like is I think there is a slide with respect. I think we'll see. I remember there being a slide about this. Maybe later it will be there. Okay, where was I? Finding x2. X2 is nothing but old point plus alpha into p. I don't have alpha. So substitute this x2 in the function value. Which function? This function. This function you substitute. Then you will get some function in alpha. Differentiate it, equate it to 0. Solve the equation, you will get some alpha. So substitute this alpha back into x2. You got your x2. Now you can use any of the three conditions. No change in x, or else no change in function value, or else gradient almost becoming 0. You can do any of these things. Okay, this apparently this is, what is this? Okay, this is a new function, new point, isn't it? Or is it just a continuation? 1 by 4. Yes, this is continuation. Apparently this condition is not satisfied, so we are iterating. We are finding x3. X2 we know, we got this as x2. We have to find x3. Before that, find p2. How to find p2? Just find the gradient at that point and up, put a negative sign because you're descending. You're doing, you want minimization. You got some direction. How to find x3? Old point plus alpha into p. You got something in alpha. Plug it in the function value. You will get some function in alpha. Differentiate it and equate it to 0. Solve the equation. You'll get some alpha value. Put it back in x3. You will get x3. Okay, we've done all of this. We've been doing what have we been doing? We got some f of x. We got some initial point. Find direction. Find alpha. Update the point. Check optimal or not. How to check optimal? Three ways are there: change in function value, change in x, or else gradient is almost 0. Here we are checking function value. Difference is, if the difference is less than some epsilon or not. Here epsilon was chosen to be 0.05. You shouldn't change the epsilon every single time. Every iteration, same epsilon you will be using. In this case, it is uh, less than 0.05, the difference. So we can say that the function values are not changing much. So I must probably be near my minimum, yes. So you can stop your algorithm here. So we are done with the algorithm. This is what this is saying. This is what it is saying. This is minimization once again. Is there a better slide? No, okay, no. Here they're checking another they're using another optimality check. No difference in consecutive points. How do you check that? You just take xk plus 1 and do minus xk. Then we are done. If it is less than some certain threshold, some epsilon, then you can declare my function is, my algorithm is, it has done its job. It is done. Okay, is this the same question? It is the same question. What is this doing? Uh, okay, it's solving it, right? Is it solved here? No. Same thing. You do everything is same. You get something in, something as a function of alpha. Differentiate it. You will get alpha. But look at this. You have to differentiate this equation, equate it to 0, and find the roots. How nice. Okay, I think this is after differentiation, right? This is the function in alpha. Differentiate it, you will get this function. Equate it to 0 and solve for alpha. That is very tedious, no? So line search is sometimes very tedious. I think it will be shown in one of the slides. Illustration of line search with gradient direction. Okay, we did line search with gradient only, no? Minimization means we'll take negative of the gradient. Okay, negative of the gradient. At what point? This is our initial point. So substitute my values over here. You'll get your direction. How to get alpha? We'll have to see. So new point is nothing but old point plus alpha into p. Old point, alpha I don't know. This is my P. My x2 is in terms of alpha. How to get alpha? Substitute in my function. If you substitute it in the function, you got something. Okay, this is the previous problem only. The same thing. uh, okay, this is the function. If you differentiate it, you'll get this one. Equate it to 0 and then solve for alpha, you will get some alpha, but this is very difficult. It is possible, but it is hard. You can't do this thing. So we might have to then leave this method because at some point it's becoming impractical. Instead of making things easier, it's making things more difficult. So we'll have to opt for some other methods. Okay, this is also another example, I suppose. It's the same thing, right? We use other techniques to find alpha 1. That means yes. Okay. Oh yes, this is the diagram I'm looking for. This plane, whatever is this plane, that is the direction of p for some current iteration wherever you are. Let's say you are here. If you notice, if you move in the direction of p, your function value is increasing. So that is what we have been doing, but using math. This is graph. So my x2 will lie anywhere, somewhere on this plane. So that is why on the output axis we have phi of alpha. Input axis we have alpha. This is the direction of p. This was what I was searching for. Nice. Yes, you have another. This is like some direction p. You're here. If you take some step length alpha, you will move somewhere. You'll keep moving closer to the maximum. I mean, p is not constant. If you go to a new point, you will get a new p. So new p will be probably in the other direction. P keeps changing in every iteration, so it's keeps changing. Okay, review. Okay, line search. Like we only did line search. We didn't do trust region. Also, very crude understanding we have. Uh, some random problem. You can try this. Okay, fine. I will end the recording now. The the other I don't think the other PDFs are there for minor tools. The other batch just mentioned it's still 19, so I'm taking their word for that. Okay, I'll end the recording now.